Okay, so let's start. So what I'm going to do is I'm going to do a full review of what you're going to have on the test, right? So you're going to have, which chapters do you have on the test? 4, 5, and 6, right? So we're going to start with chapter 4 and talk about some of the details that I'd like you to really fully comprehend and integrate into your thinking from chapter 4. So chapter 4 are the key ingredients of inferential statistics, right? And what are the key ingredients? What do we use in inferential statistics? What's the big thing we use? Come on, guys. The z-score, absolutely. So the z-score is built around the normal distribution. And the normal distribution has certain features that, when taken in line with probability, allows us to do inferential statistics, right? And one of the most important features that you're going to recognize and you're going to learn about in chapter 4 when you reread it is the idea that if you think of this distribution as representing the whole population, you can determine the probability of randomly picking a single score out of this. The probability you can determine the probability of randomly picking a single score out of this distribution. So let me give you an example. What's the probability of picking a score that is between -4 standard deviations and 0 standard deviations, i.e. between -4 z-score and a z-score of 0? What's the probability of that? It's what? 50, absolutely. So we know that this distribution, the z distribution, has a mean z-score of 0, and as you go further and further to infinity, you're getting into the -5 and -6 z-score, and therefore you know that the probability of picking something from this region is 50%, because that's half of your distribution. Everybody okay with that? Similarly, the probability of picking something from this half of the distribution is 50%. However, we have the ability, because this is a mathematically determined distribution, we have the ability to tell exactly what the probability of randomly picking a score from this distribution between any 2 points of the distribution, any 2 points. But we have the tradition of dividing the distribution into 1 and 2, +1, +2 standard deviations, -1, -2, and then we can actually put some percentages for these. This is 34%, this is 14%, and this is 2%. And similarly, this is 34, 14, and 2%. Everybody with me on that? So given that fact, what is the probability of picking a score at random that is between 0 and +1 standard deviations? 34%. What's the probability of picking a score above 2 standard deviation above the mean? 2%. So above this is 2%. Great. And you could transform a z distribution. If you have a raw distribution, a raw score, a set of raw scores that are normally distributed, you can transform any raw score to a z distribution. And the transformation is simply z equals x minus m over sd. This is the transformation. So if I give you a test, let's say I had 100 people in this classroom, and I give you a test, and I tell you your standard deviation is 5 and your mean is 2, and I give you your own score. Let's say I give you a score of a 3. You can automatically transform that into a z-score and tell where you fall in that distribution. So let's try that. Let's actually make it a score of 4. You got a score, your score, x, is 4. The mean is 2, so 4 minus 2 over 5. 2 over 5. So your z is 2 over 5. Okay? And you can then plot that z into the distribution. So here we go. Okay? So you've got a plus 0.4. Sorry, that's a 5. Thanks. I should have it for the camera, just right. Okay, so it's a 5, and we are looking at a z-score of plus 0.04, 0.4, excuse me, plus 0.4. And that puts it right here. So your z-score is 0.4. Can you go ahead and tell me how many people have done worse than you on this test? If your score was a z-score of 0.4, what percentage of people scored below you on this test? So what would you do? Go ahead, try it, and then I'll explain it to you. Yeah, below. Somebody says 64%, 65. Okay, so what you do is you go to your z table, and you are looking for, yeah, 0.4. You're looking for a z-score between the mean and 0.4. So 0.4 gives you a percent equivalent. 0.4 is 15.54 between the mean and the 0.4. So 15.54. Should move it a little bit here. It's closer to 0.5. So this percentage here is 15.54. And then you add this, since I'm asking you about below this point, you add this to 50% because that's the remaining part. So you add that to 50%, gives you a 65.54. Okay, so that's the percentage of scores below yours in the classroom if the distribution was normal. Okay, so you can see you can determine different things. You can determine percentages. And since you can determine percentages, you can think of this distribution as a probability distribution. So it's a frequency distribution, we know that, but it also has another name. It's a probability distribution. And it's a specific type of probability distribution. It's a z distribution or a normal distribution.
Where did you get the 50 from?
Where did I get the 50?
Yeah.
You see, you're looking at, first of all, you look at the table to look at percent between the mean and this score, gives you 15.54. And you have to add to it the other half that isn't given to you. So the other half is 50%. Okay? Does that make sense? Okay. So as I was saying, this is a probability distribution. And what it means is that you are looking at, you can actually transform whatever you're looking at to probabilities. If I ask you what's the probability of picking a score below yours, you would say 65.54%. There is a 65.54% that if I randomly selected any score below yours, excuse me, if I give you a score below yours and I ask you what is the likelihood of you having picked that score, you can tell me that it's 65.54%. Because you can think of this distribution as having, as a whole, a probability of 1. Meaning that if I ask you, what's the probability of picking any score between 0 and 100 on this test? Well, it's going to be 1. It's 100%. You're 100% going to be able to pick a score from 0 to 100 if that's the range of scores. But you can also tell me what's the probability of picking a score below the average. If the average is, if the mean is 2, what's the probability of picking a score below 2? 50%. Below 2. If the average is 2, right here. This is the raw score. You have to think of raw scores versus the average is 2. If your average is 2, then you have 50% chance of picking a score that is below 2, sorry. And you have 50% of picking a score below, above 2. And similarly, if the mean is 2 and the standard deviation is 5, then you can sort of add 2 plus 5 gives you the first standard deviation level, that's 7. And then another 5 will give you 12. And you can tell me what's the probability of getting a score that's above 7. What's the probability of getting a score above 7 on this test? 16. It's 14 plus 2, 16. So you can see you can transform probabilities into percentages. These are all interchangeable concepts. But the fundamental thing that you need to take from this chapter is that given a z distribution, you can automatically ask the question of what is the probability of getting a specific score from this distribution if you randomly selected a single individual. Okay? Okay. So given the nature of the z distribution, and given the fact that you know mathematically all the probabilities in a z distribution, you can ask questions like, what is the probability of getting a specific score or a specific score below this point or a score between 2 points on a normal distribution? What is that probability? You can find out that probability. So for example, you remember that example of a single baby? Okay. The big thing with the single baby is to ask the following question. We wanted to find, we had a distribution of babies who took a vitamin, and they walked at an average of what, 14 months? With a standard deviation, the mean was 14, and the standard deviation was what? You remember? It's in the next chapter. 7, was it? No, not 7. What was the next chapter? 14. The standard deviation was 3. So standard deviation of 3. So babies, normal babies, taking that vitamin, walked at an average age of 14, and with a standard deviation of 3. So 14, 17, 20, and 11, and then 8. These are the raw scores, and the equivalent z-scores are -2, -1, 0, +1, +2. Okay, so we wanted to ask the question, what if we simply randomly selected a single baby? If we simply randomly selected a single baby from this population, from this distribution, what is the likelihood that that baby would have walked at the age of 8 or below? It's less than 2%. Absolutely. It is less than 2%. Let's move to chapter 5 and review chapter 5. And in fact, we have started to review chapter 5. Because one of the questions of chapter 5 is the following. So there's a bunch of researchers who took a vitamin and decided to give it to a whole bunch of babies. And they actually now have knowledge of how babies on that vitamin walk. So the hypothetical in this chapter is that you've got a distribution that some group has total knowledge of. That's their population. So they're like a god. They actually know everything about that distribution. They know the population. That's usually not the case. We don't know the population. We are making inferences about the population. But in this case, let's assume that you know the population. And because they know the population, they decide they want to use inferential statistics to sample from that population. And they want to test a question about the supervitamin, this very purified vitamin. So they take a single baby at random from this from this distribution. They simply pick a baby at random from this distribution, and they give that baby a really special fortified vitamin. This is above and beyond what they've been giving him or giving them, right? They give that single baby a special vitamin. Now, although we are dealing with a single baby, we're thinking of that single baby as the sample. This is also a simplification of the process, but it's a simplification to show you at the very skeleton, bare minimum, how inferential statistics works. So you take a single baby and you ask the question. And you give them that special vitamin, you give them that fortified vitamin, and you ask the question, if we had picked that single baby from this distribution, and that special vitamin did not really have any effect, what is the probability of that single baby's score being whatever it is? Okay? So you can listen to that statement on the video because it's a complex statement. But the question is, given the question is, what is the probability of getting such a score, whatever it is? Let's say the score of that single baby, X, the score was he actually walked at the age of 7 months. Okay? So that single baby walked at the age of 7 months. The question to ask is, we've picked a baby from a population. That population was getting the regular vitamin, and we gave that single baby a special fortified vitamin. What is the probability of him having walked at 7 months had the vitamin never had an effect? Meaning that if the vitamin had never had an effect, what's the probability of the baby walking at 7 months? Can you tell me? Less than 2%. It's clearly less than 8. It's less than 2%. Okay? So that is fundamentally the question behind every hypothesis testing procedure we do in statistics, especially when we are testing the null hypothesis. So let's go step by step on the 5 steps of hypothesis testing and talk about why we do each of these steps. Okay? The first step in hypothesis testing is the following. I'm going to erase this. And the first step of hypothesis testing is to restate the question as a research and null hypothesis about the population. So for your tests, I do want you to write this down for every step. Restate the question as a research and null hypothesis about the population. So restating the question can be done in a formalized way. You first define your population, POP1 and POP2. POP1 is your experimental population, right? Or what you're going to be doing things to. And POP2 is what your general population, what the null looks like. So this is your sort of control. This is not really what the book describes, and it's not technically the perfect explanation, but this is to simplify the process. So this is what you're going to be experimenting with, and this is what is the normal case. And then after you define POP1 and POP2, you develop your hypotheses based on these populations. So your null hypothesis is defined as H hypothesis with a null, a phi, and your alternate hypothesis or research hypothesis, HA. So in this case, your population is what? Anybody? In the case of the single baby?
Babies who take the...
Excellent. Very good. So you always go to the population. So you take the single baby, and you know everything about the baby, so that's your sample, but you want to make inference about a population, the population from which that baby would have come. So that's babies who take the fortified vitamin. And then population 2 is what? Babies in general, very good. Babies in general. Babies in general, who take the normal vitamin, who take the non-fortified vitamin. Because you remember, we selected from this population, they were taking regular vitamins who take non-fortified vitamins. Okay, so now we need to ask the question, we need to phrase the question or restate the question in terms of a research and null hypothesis. And it's easier actually to start out with the thing that a researcher would normally be asking. What would you naturally be asking as a researcher? You'd be asking, well, is that baby that we've given the special vitamin going to walk at an earlier age? That's fundamentally the question. So that's your alternate hypothesis. That's what you're truly deep in your heart want to prove, that, hey, this vitamin works. So your alternate hypothesis is babies who take the fortified vitamin, POP1, their mean, but since it's a single sample, it doesn't make sense to talk about means, but their mean would be less than, since it's about walking earlier, right? Walking earlier means their month at which they walk is going to be less than. So you have to think about these. You have to sort of conceptualize it and think, oh, what's walking earlier? Oh, yeah, they'll have a smaller number representing the age at which they walked. So their mean would be smaller than babies who do not take POP2M, who do not take the fortified vitamin. Everybody okay with that? Again, the process here is to think about what you're doing. The null hypothesis, on the other hand, will be the exact opposite of this. And these two have to fully cover every possibility. So when you have greater than, what is the opposite of greater than that covers the whole range of possibilities? Exactly. And if you have less than, then it's greater than or equal. So POP1 mean is going to be greater than POP2 mean. Okay? If you simply substitute, it'll make sense too, because that's how the book does it. It doesn't do it using these notations, but these notations are exactly the same. This is telling you, the null hypothesis is stating that babies who take the fortified vitamins either stay the same, they're not different from babies in general, or in fact become a little bit more retarded. They walk at a later age. So I mean, that's a bad thing, right? On the other hand, the alternate hypothesis is that babies who take the fortified vitamins will actually walk at an earlier age than babies in general. Everybody okay with me? Okay, so one of the questions is, why do we do this? First of all, let me ask the question generally. Why are we restating the question in terms of the population, or about the population? Why are we doing it about the population? Why don't we just look at it as a sample? Any thoughts? Yeah.
Because ideally we would have enough money to support more of a experimental sample, but in this case you can't. So.
Okay, so you want to increase the size of the sample. Correct, but there is a more fundamental reason. Yes?
Because the population includes all of, like, there's not an outside variable really? So it's larger groups, so
Well,
can't
sort of. It's actually because of the fact that we are not interested in the sample per se. When we are doing a drug study, we're not just interested in the people that we've just put in the experiment. We're really trying to predict how this drug will work with people in general, outside the experimental situation, right? So the sample we actually have knowledge of, we know what happens to them, but what we're really trying to do is make inferences on how this drug would work with other people. Okay? So we know everything about the sample. That's what we're going to use to actually make decisions about how we infer the drug will work with other people. So we make these decisions, we make them about the population. We don't make them about the sample, because in fact, we have everything we need to know about the sample. We know how the single baby actually walked. We know he walked at 7 months. So there's no inference about him. We know the facts about him. We make inferences about the population because that's our objective. Our objective is to think about what is happening what would happen if we give the drug to other people. Everybody with me? Any questions about that? So we clearly need to make the question refer to the population in general. And why do we do this weird thing where we try to reject the null rather than try to prove the positive? Yes, Arian.
Because if we reject the null, then we automatically know that it didn't pertain to the actual experiment, that it was just for some reason, there was an extreme.
No, not exactly. Not exactly. No, that's not the right answer. You know, you're on the right track, but that's not the right answer. Yeah.
By disproving the exact opposite of what you're trying to prove to your research hypothesis, kind of provide like, well, it's not the opposite of the situation, so you verify that it could very likely be the actual.
Very good, very good. And extend that thinking. But why are we doing it in this opposite direction way? You want to try again? Why are we doing it backwards?
Because there's no causality in statistics.
Because there's no causality.
Causality, so you have to, you can't prove, so you have to disprove the opposite.
It's not about causality. Yes, I see where you're coming from when it comes to causality. It's not about causality, but you're on the right track. You cannot prove 100% that something is like that. So you have to reject potential hypotheses. Who else wants to add to that? Remember Karl Popper? What did Karl Popper say? Modus tollens, right? The idea that the way you work science is you work it through falsification. You falsify certain concepts. So you throw out a hypothesis and try to test against it. And by testing it against it, you are likely to approach concluding this. You don't have 100% evidence for this. You simply try to add more and more evidence in support of this by rejecting null hypothesis. So this is one reason. What's the other reason? The book? OK, so what's the other reason? The book actually talks about a reason. Go ahead and look at that section on the logic of hypothesis testing on page 147. It's actually on page 148. And if you want to read it, it's the first complete paragraph. So without such a tortuous way of going at the problem. Actually, sorry. If you go to one paragraph before that, the thinking starts there. OK, let me highlight to you the section that you really need to fully comprehend for the test. The idea here is, if you look at OK, so this kind of testing, which is the opposite of what you predict, is a roundabout reasoning, is at the heart of inferential statistics. It is something like a double negative. One reason for this approach is that we have information to figure the probability of getting a particular experimental result if the situation of there being no difference is true. Okay, so this is a very important sentence. We do not necessarily know the situation where the drug has an effect. We don't have knowledge about what would it look like, what would the distribution look like if the drug had an effect. We only truly know the situation under the null. Okay, I'm going to repeat that. We only truly know the situation under the null, meaning under conditions where the drug had no effect. So we know this population. This is your comparison distribution. And I've called it before a distribution under the null. This is the condition under which the drug had no effect. And this is what we would necessarily have direct knowledge of, or more knowledge of, let's put it that way. So since we have knowledge or more knowledge of the condition under the null, we create a system in which we reject the condition under the null. We say, oh, you know, if the drug had no effect, okay, the probability of getting such a score is so low that I don't think the drug had no effect. And therefore, you reject the null. By saying that statement, you're rejecting the null. So, you bet. So, you are basically saying that that this is I've given this drug to this single baby, and I say to myself, well, given the score of 7 months, for example, okay, I think this score is so extreme that I don't think this single baby is represented by this distribution. The probability of him, or the probability of him walking at the age of 7 months, if the drug had no effect, is less than 2%. Therefore, I think I can reject the idea that the drug had no effect. I can reject this null hypothesis, and I can reject the associated distribution, and I can start thinking of this baby as coming from a different distribution, a distribution that represents babies who have been affected by the drug. We don't know. We didn't even draw that distribution because that's a distribution we had no knowledge of. We were testing this. Testing against this distribution. This is our straw man. We rejected it, and now we think of the baby as coming from a different distribution. That, in fact, he doesn't fall into that distribution. He comes from a different distribution. Does that make sense?
What would be our next step after that? Will we create another hypothesis, or?
Oh, no. So you basically say you reject the null, and now you have evidence that you have statistical significance in terms of that the babies who took the fortified vitamins walked at an earlier age. And what you do in a scientific study is you try to replicate it. You try to do another experiment, although that's rarely done. You try to do another experiment in which you replicate it to see if this was, again, you know, not, I mean, still there's a 5% chance. Let's say you set your significance level to 5%. So there's 5% chance you could have gotten this by pure chance. So you replicate it. But, you know, typically you're happy with the results if you can reject the null. Yes?
In the case of like vitamins, if you reject a null,
Mhm.
say any type of vitamins being given out to the population, is that when if someone's working on a certain type of product to get out to the people,
Uh-huh.
is that something where they completely start to experiment on a whole other type of drug? Would that be a reason to move on?
Yeah, I mean that's you could move on from there. You could yeah. Well, if you can't reject the null, then you basically cannot sell the drug as effective because you couldn't reject the null. Yeah. So let's go to the next step. How are we doing on time? Good. Thank you. So let's go to the next step. So the next step is really the crux of hypothesis testing. And I'm going to erase this. And the next step is determine the characteristics of the comparison distribution. Basically, give me the straw man against which I'm going to test my sample. Okay, determine. This is step 2. Determine the characteristics of the comparison distribution. And remember, from a technical point of view, you need 4 characteristics. What are the 4 characteristics? Very good. Mean, variance, standard deviation, and shape. Excellent. And in chapter 5, these will be given to you in the problem. They'll be stated for you because God knows the population. So they're going to just be stated for you. So in the case of the baby, what's the mean of the comparison distribution? 14. What's the standard deviation? 3. What's the variance? 9. It's square root of 3 squared. And what's the shape? Normal. It was given to you. So it's easy in chapter 5. In chapter 6, it becomes a little bit more difficult. So that's step number 2. And why do we do that? You remember, the really important thing to do here is to think about these steps and think about the reasoning behind them. What's the reasoning behind the comparison distribution?
Find the cutoff.
To find the cutoff. So that's the technical reason. Conceptually, I just sort of explained to you the conceptual reason for the comparison distribution. This is, yeah. Yeah, yeah. Oh. So any answers? Why are we doing it? You can just sort of restate what I just said a few seconds ago. Yeah.
So that we can hopefully reject the no.
Yeah, absolutely. That's the overall objective. But why do it with a comparison distribution? What's the purpose of the comparison? Yeah.
Is it to be able to like see it, I guess?
Yeah, yeah. And it's basically a distribution that tells you how things would look like if the thing you're trying to do, if the intervention, treatment, isn't working. It's your straw man. How would things look if the thing you do isn't working? This is how it's going to look. So you're going to test against this. You're going to test against it. And you are initially also have sampled from it. This is the distribution you sampled from, and then you're going to do something to that little sample, and then you're going to test against it. Yes?
So that's what the null is.
Exactly. This is called the distribution under the null. This is the distribution under the null. Okay. So let's go to step number 3. Step number 3, who wants to tell me what step number 3 is? Okay. Determine the cutoff sample score. Determine the cutoff at which determine the cutoff. How does the book phrase it? Determine the cutoff on the comparison distribution. The cutoff on the comparison distribution at which the null hypothesis should be rejected. Excellent. Okay, so you need to come up with a specific cutoff at which you're going to say, look, given this probability, given the smallness of this probability, I can reject the null. How do you determine this? Anybody want to tell me how do you I mean, I know that basically I'll be giving it to you in a problem. But if you had to think about it, what are the two factors? There are two factors that play a role in determining the cutoff. Rachel. Yeah, that's technically what you would be doing, is simply take the statistical significance I give you, like p less than 0.05, and based on that you would determine it. But conceptually, what do you do in order to determine that? What are the two factors? Yes, sir. That's another factor, yeah. One or two-tailed, that's another technical factor. But again, I'm looking for the conceptual factor. How do you determine the 0.05? How do you decide that we should actually pick a 0.05 level, not a 0.001 level? By how careful you need to be, absolutely. By how careful you need to be, how conservative you need to be. Who wants to tell me what are the two things that play a huge role in that determination? The errors, excellent. And what are these two errors called? Type 1 and type 2 errors. Type 1 and type 2 error. What is type 1 error? being
No, not conservative enough.
not conservative enough. Type 1 error is what I call the big error, the scary error. It's number 1. And it's what scientists really want to avoid. It's the type of error in which you say things are working, but in fact they're not working. So who wants to translate that in terms of the null hypothesis? It's the error where you say things are working when they're not working. What are you doing? Are you rejecting or not rejecting the null? You're rejecting the null when it shouldn't be rejected. Meaning you're saying, oh yeah, the drug works when it's not working. Well, that's the worst error a scientist can handle, because basically scientists are very conservative, stick in the muds. They they don't want to deal with any chances of saying something and looking bad. And in fact, they also don't want to hurt people. Most drugs have an impact that are side effects, and they don't want to do that. So that's type 1 error. And type 2 error is what? Failure to reject when you should reject, meaning you are basically saying, oh, there's no effect, but in fact there is an effect. We can live a little bit more with that error than the first type of error. And it all depends on the implications of your study. If you're studying something that could be extremely harmful. So going back, type 2 error is failure to reject when in fact you should reject, i.e. saying that the drug had no effect, when in fact you should be saying, oh, the drug actually is effective. And as I said, you can live more with that than the first type, the type 1 error. And it all depends on how harmful using that drug is to people in general. I mean, drugs have side effects, right? And if you're going to give this drug to thousands and thousands of people, some people will have side effects and could suffer from them. So you really don't want to make an error when something is a type 1 error, when something could have such significant effect on people. You can live with more error if you can guarantee that somebody else will replicate and remove that potential of error, right? So it all depends on where you stand. And obviously, when teaching basic statistics, I'm going to just give it to you because we don't want to go into the details of every scientific experiment. But that's how you make a decision, based on type 1 and type 2 error. You have to remember those two concepts for the test. OK, so I'll give you like 0.05, and I'll ask you for one-tailed. OK, so let's take this level, 0.05, and it's one-tailed. We know it's one-tailed. How do we know it's one-tailed versus two-tailed? If it's greater than or less than, you're asking about a one-tailed question. You're asking a one-tailed question, meaning if you're asking, is this going to increase or decrease something? Is this going to make people or babies walk at an earlier age or a later age? That's a one-tailed question. If you're asking, is this making any difference, whether making them walk earlier or later, that's a two-tailed question. Now, the book suggests that people should go for two-tailed questions in general, or even like set things up as two-tailed, because of the fact that two-tailed is more conservative. Can anybody tell me why two-taileds are more conservative? Exactly. There is less margin for error on either side. And why is that? Can you answer? Yeah, you can go. You can go ahead. Is it Jordan?
Yeah.
Yeah, Jordan, go ahead.
Well, because you split the percentage in half.
Excellent. Because in two-tailed, you split the percentage in half to each tail, and that automatically pushes the. So if you have 0.05 here, i.e. 5%, 0.25 is here, that's 2.5%, and therefore you need an more extreme score to reject the null as opposed to a less extreme score. See, here's where you would reject. If something fell here, you can reject it at the 0.05 level, but you cannot reject it at the 0.25 level, right? Because it's here, not beyond this. It's just beyond this. So you can see you become more and more conservative when you use two-tailed. And there's a regular suggestion to use two-tailed. But if you have a theory and you know and you don't care about the other side, like if you happen to have if you do the drug study and you discover, in fact, it's making people walk at a later age, well, if they walk at a later age or at the same age, it doesn't matter to you. You know the drug had failed. So you should go for a one-tailed. However, you might decide to go for a one tail that is even more conservative, just for the sake of being conservative. But given the fact that if they walk at this age or this age or this age, it all means that the drug has failed, you're better off using one-tailed. It's more logical to use one-tailed. But your determination of what cutoff to use should be conservative because it's a drug. Everybody with me on that aspect of things? Any questions? Any thoughts? OK. So I give you a 0.05, and it's one-tailed. I ask you, go ahead and find for me the cutoff score at which we can reject the null. So go ahead, do that for me by looking at the table.
One or two-tailed?
It's going to be one-tailed, since it's walking at an earlier age, at the 0.05 level. It's one-tailed. We're going to stick with one-tailed for this one. OK, so 165, 164. So you basically need to find percentage entail of 5%. So you go to the table, and you go down to percentage entail 5%. So you go here, percent entail. You keep going down until you reach 5%. And we don't have exactly 5%. We have 4.95, 5.05. So you sort of want the middle ground, but you don't have the middle ground. The computer will do it for you. We'll give you the exact p-value. I mean, the exact z-value, but we don't have it here. So go for more conservative. A more conservative cutoff would be 4.95. OK, that's a more conservative cutoff. So your cutoff should be at a z-score of minus 1.65. So let's say 5% is 5. This is 2%. So 5% will be somewhere here, and it is minus 1.65. OK, minus 1.65 is your cutoff. Everybody OK with that? Go to a more conservative spot. Now, next would be to do step number 3, which is what? What is step number 3? Oh, sorry, number 4. Number 4. Determine your sample z-score. Or you determine your sample z-score, or determine your sample score on the comparison distribution. And basically, it is finding out your own sample z-score. And to do that, you've done that in the past. Your z is equal to your x minus m over sd. Your z here is x, which is 7 months, minus the mean, which is 14 months, over 3, your standard deviation. And we're looking at minus 7 over 3. And that is 2.33. And it's negative 2.33. So this is your z-score. And now you plot it into your comparison distribution. That single baby score actually comes from right here, and it is minus 2.33. Oh, wow. OK, so it's pretty extreme. What this is telling you is the likelihood of us having picked that baby by chance is quite less than 5%. So your last step is determine whether to reject the null or not, right? Decide whether or not to reject the null. And in this case, we do reject the null because this baby, had the drug had no effect, the likelihood of us picking that baby is so low that we do not think the drug had no effect. OK? So again, let me repeat one more time what we always ask when we're doing hypothesis testing. We are asking, what is the likelihood that we would have picked this baby with this special score, or this sample with this special score, had the intervention or treatment had no effect? So we always ask that question. What is the likelihood of this score had the intervention had no effect? The likelihood is less than 5%. Therefore, we really don't think that the drug had no effect. We think the drug probably had an effect. So we reject the null. So in this case, we reject the null. We don't accept the null, or we don't accept the alternate. We reject the null. That's all we say. And based on rejecting the null, we think that most likely the drug had an effect. Okay? We don't say we accept the null. And we never say we accept the alternate. We always say we reject the null or fail to reject the null. Those are the two options. And the reason we say that, again, there are many reasons. One of them is we want to be conservative about our decision making. We are able only to reject or fail to reject because somebody else might do this and they could reject it given the characteristics of the error involved. Okay? But we are now building evidence that most likely this drug has an effect. Everybody okay with this? Wonderful. Okay, so you're going to do great on the test. Anybody has any questions about this chapter, chapter 5? Okay. So how are we doing on time for this one? 10:20. Okay. We can stop it. Okay. So let's talk about chapter 6. Okay. Actually, before we do that, let's just build our little glossary up, right? We have a huge glossary of terms. And we need to make sure everybody's on board with all the terms we're going to be using for the rest of the semester, right? So, we've got a sample. And the sample has its own features. It has its mean. It has its own standard deviation. It has its own variance. And these are called sample what? What are these called? Sample, when you take... Yeah. Statistics. Sample statistics. So you've got sample statistics, and then you've got population what? What are the features of a population that we would be interested in? So for example, the distribution, the comparison distribution, has its own mean, its own standard deviation, its own variance, and a shape. What are these called? Population? Starts with a P. What? No. Parameters. Excellent, Aron. Fantastic. So population parameters. Population.
Yeah, that is a strong marker.
Is it?
Yeah.
Isn't it? Okay, let's use the black one here. Okay, so the population parameter will have features like this. So we call it pop. We give it pop M, like the mean of the population. Pop SD, which is the standard deviation of the population. Pop SD squared, which is the variance of the population. The sample doesn't get that. It doesn't get a pop in front of it. Everybody sees the difference between a sample and a population. These are the notations for a population. Now, when you go and move from a population of original scores and develop a sampling distribution, you go to a small m next to these parameters. So pop mm, that small m here, reflects that it's a sampling distribution mean. And pop SDM and pop SD squared m. So these reflect that it's from a sampling distribution. So let's talk a little bit about what we're doing at this point in chapter 6. Who wants to start me off? What is the big change in Chapter 6 that we have added over Chapter 5. Yes?
The bigger sampling size?
The bigger
Yeah,
sample,
it's not
yeah.
a
So the
sample
sample moves from a single baby. We used to have a single baby, and now we have a bunch of babies, maybe 5 babies. Okay? And similarly, we move from a distribution of single babies. That distribution we were looking at just a few minutes ago, looking at babies who have taken regular vitamin. This is the comparison distribution. Now, we were comparing the single baby to a comparison distribution made out of single babies. Now that we have a sample made out of, let's say, 5 babies, n equals 5, meaning a sample size of 5, we can't use that same distribution as our comparison distribution because of the fact that comparison distributions have to match what you're comparing to. So you have to use a distribution made out of samples of 5 babies. So your distribution here will be means, I can't stop as I said. So it's going to be a distribution of means of samples. Everybody okay with me? So here you've got a distribution of single babies, and here you have a distribution of means, okay? Because you're comparing the mean of a sample of 5 babies to a distribution of means. That distribution of means has another name. It's called a sampling distribution of means, or a sampling distribution for short. Everybody okay with that? So the new thing we've added to this chapter is that instead of looking at a simple distribution of single scores, we have moved to another level. We are now using a comparison distribution made of a distribution of means. And how do we derive this distribution of means from a distribution of single scores? The way we derive this is through a process of sampling over and over again from this distribution. And here's where we use the demonstration online to really get a sense of how this is done. So I'm going to take off this microphone and show you the process by turning. So this is a demonstration. How many of you actually have used this, have played with it over the... Only 3? I begged. Didn't I beg? Please.
I was playing with it for hours.
You did?
Yeah, no.
Fantastic. I'm not going to go there. I know what you were laughing about last week. So let's talk about this demo. This is a demonstration of how we build a sampling distribution. And the demonstration shows you, let me put this in the middle. Would you turn, Gino, would you turn the light, one light off? Yeah. Actually, the other one, if you could. Let's see. Yeah, that's good. Does it look better now? OK, great. So as you can see, you've got 3 levels here. You've got an original population made out of single scores. So this is, think of it as the single babies, right? Single babies, single scores. And then you're going to sample from this distribution, and you're going to build a sampling distribution. So when you do that, you build up a distribution of means. And this is what its name here, distribution of means. Now, let's do that using a sample of 5 and see what happens. We're going to set this to a sample of 5, as you can see here. That's 5. And we're going to run an animation. OK, so it picked 5 scores, and it put the mean of these 5 scores here. And it says the mean of these 5 scores is 13.29. The mean of the original population was 16. So 13.29 is a bit off, right? And the way you can tell it's off, it's about half a standard deviation off. So it's the standard deviation is 5. So it's about half a standard deviation off the original. So if we do it again, Oh, look at that one. That one was right right a bit on spot. And the average of both actually gets you to a mean that is getting closer to 16. So you see the mean is 14.51, and here it's 16. And you can see what happened here. The way it worked is you got a score here. You got a score here to cancel it out, getting it in the middle. Another score that is extreme, a score that cancels out, getting in the middle. But this score didn't get canceled out, so it was pulled, the mean was pulled up a little bit. So if you do this over and over again, you build a distribution. You can see here, this shows you the difference between the current mean and the original mean. The original mean is in blue, and the current mean is in red. So it's getting closer. Even with like three attempts or 3 means, you're getting closer. And if you do it more, you're going to get really closer. You see how it's building? It's building up. So let's run it 5 times, 10 times, no, 25 times. Let's run it 10,000 times. It builds up a distribution that's normal in shape, and that has a mean right on top of this mean. So the mean here is 15.97, and the mean here is 16. If we run it 10,000 times more, 15.98, it's getting closer. 15.99, and 15.99 still, it's not moving. 16, yes! And that actually hit the mean on the spot. Yeah, that's right. The 70,030. Now let's do it. Yes, sir.
What was the kurtosis again?
Kurtosis. Who wants to tell me what kurtosis is? Is that a disease? No. It's the thickness of the tails. Remember, the thickness of the tails. Now let's do this, but instead of, yes, sir. Kurtosis. And let's do this with an n of 25. Okay? And anybody want to guess, is the mean going to be very close this time, given the sample size? Yeah. And you're going to tell me why, as you increase the sample size, you get a better approximation of the mean. More data, excellent. And why is more data better?
Less room for error.
Less room for error, very good. And a bit more specific. There's more chances, Jordan?
The extreme scores balance each other out.
Excellent. There are more chances that these extreme scores balance each other out, resulting in a convergence towards the middle. What is that theorem called? It has a name. The central limit theorem. Okay, so as you look at multiple little random effects coming into play, as they build up, you converge towards more and more the mean. And yes. So well, I explained it last week, and I explained it this way. I said the idea is that in nature, things balance out in such a way as to create a normal distribution of naturally occurring phenomena. What did I give an example of?
Yeah.
I gave an example of a specific human attribute, biological attribute, height. Height, exactly. And the way I explained it was that height, anybody's height is determined by a whole slew of factors. These factors could be your genetics. That's one of the bigger factors, right? But it could be anything that happened to you throughout your development. It could be even before your birth. So it could be your maternal nutrition, your mother's nutrition, how much she experienced stress in utero, the hormonal state inside of her. Then when you were born, did you get good nutrition? Did you get enough oxygen throughout the period when you were being birthed? And then later on, did you have good nutrition? Did your hormones get affected by environmental factors? Did you eat heavy meat with hormones included in the meat, for example? There are many, many possible variations on why or what would affect your height. There are main ones, like your genetics and so on, but there are many other little variables. Those are called random variables that on their own, they're going to balance each other out. So things like, whether you've had a great nutrition during your development might balance out with your mother being stressed during when she was pregnant with you. These things overall don't work in one direction or another. They balance each other out. You would be a really unlucky person if everything worked against you. And I demonstrated that by using die, right? I picked 6 die, and I said, well, what is the likelihood of me throwing these 6 die and getting 6 sixes? It's very low, right? To really have everything work for you to get 6 sixes is a low probability. On the other hand, to get the middle ground, so we're talking about 36, half of 36, to get half of 36 is a high 18. It's a high probability because you could have any variation building up to 18. So when you're throwing die, you're not going to get all ones, and you're not going to get all sixes. You're going to get a whole balance of different numbers, and these will always converge towards the middle number. So if you're looking at 6 die, they're all going to converge towards 18. At some point, you are going to score 6 sixes. If you throw it long enough, you're going to have a few 6 sixes and a few 6 ones. But most of the time, they're going to converge. And the idea is that in nature, that's how things are, too. That in nature, things converge towards the middle because these random factors all cancel each other out, typically in a single effect, like height. Everybody understand that concept? And that's why most things in nature follow a normal curve. A curve where the extreme scores are much rarer than the middle scores. OK, so and similarly, what you're seeing here is a similar effect, where the more there are random variables, the more likely it's going to converge towards the same mean. And you can see it was 16.76. So I just need to do it twice, and we're going to get really close to 16. Here we go. It's getting closer. So twice, got it to 16.36. And you can see how these extreme scores get balanced out. And 16.28, and it's coming closer. So if I run it 1,000 times, it's going to be 6.02. So the bigger your sample size, the more likely you're going to get closer to the mean faster. And also, what did you notice? Notice this. So I'm going to just run this 10,000 times, and you get this shape. And if I go to a sample size of 2 and run it 10,000, I get this shape. What's the difference between this shape and this shape? It's thinner. What does thinner mean in statistical terms? Higher probability. Thinner is, what is? Fewer outliers. And so what's the parameter that variance? The variance would be, if it's thinner, the variance would be smaller. So you can see when you look at a sample size of 25, the sampling distribution of that, the standard deviation and variance will be smaller. So thinner means less width in the distribution, meaning it's going to be smaller variance. Okay. So SD and SD squared will be smaller.
So the higher n gets the smaller SD.
Exactly. Higher n gets smaller SD. So we now have discovered on what principle the relationship will be between the variance of this distribution compared to the variance of this distribution. It's a relationship that's a function of sample size, meaning that the variance of this distribution is equal to the variance of this distribution divided by sample size. So let me write this down. I'm going to write it here, although it's outside. So pop SD squared m, the variance of the sampling distribution, that small m means sampling distribution, is equal to pop SD squared over n. So if you look at this, this formula, it's telling you that the variance of the sampling distribution is going to be related to the variance of the original population, and it's going to be related to it as a function of sample size. The bigger the sample size, the smaller the variance of the sampling distribution. Yes, sir?
That's what the little m just means,
The sampling distribution, exactly. That little m stands for the sampling distribution.
Bigger the sample size.
Yeah, the bigger the sample size, the smaller the variance of the sampling distribution. And you can see it here. When we put n as 25, this shrunk in width. When we move it to n of 2, when we change it to n of 2, and we run it 10,000 times, it's going to be thicker. And this is telling you that the variance of this, the width of this, is going to be in proportion of this and a function of sample size. The bigger the sample size, the smaller the width, meaning the smaller the variance. Let me just emphasize a concept that will help you remember what variance is. I don't think you've totally grasped intuitively what variance is. Variance is the spread. It's the spread of this distribution. Variance of this distribution, it's spread. That's basically what variance is. Spread. Yes, sir. Okay, thank you. Okay. I'll charge it at the break. Okay. So we've got the distribution down. Now, another thing to recognize is your mean of the sampling distribution will be very close to the mean of the original population, to the point where it's actually the same. So when you run a sampling distribution 10,000 times, the mean is here is 15.99. The original mean is 16. And that's why the second formula that you learn in the book is pop mm, meaning the sampling distribution mean, is equal to pop m, the sampling distribution of the original population. Everybody see that? Yes.
Okay, so when we, like with the homework,
Yes.
when you get to the point where you have to subtract the m from pop mm,
Uh-huh.
what mean are you using? Because if they're equal,
Excellent.
then you're not going to be, you're going to be getting.
Okay, that's an excellent question, and I'm going to answer it in just a second.
Okay.
But I just want to finish up the demo and turn it off, and that way we can go back to the board. So you can see here a few things. You've just seen in front of you how the distribution of this relates to the distribution here, and and specifically the variance of this relates to this, and the mean relates to this. The other thing that you have to recognize is the shape also is related. So, and the relationship is a funny relationship. Regardless of the shape of the original population, the shape of your sampling distribution or distribution of means will always be what? Normal. So except, here we go, I just ran it, and it's normal. And I can make this bimodal, and it'll still be normal. Look at that. It's continuously turning normal. And you can play with it and look at it in animation. Here we go. So you can see, even when it's bimodal, you're going to get a balancing out of these scores, resulting in a normal distribution.
Okay. What determines that it's normal?
OK. Yeah, so normality is based on the shape. So this is a normal distribution because it's bell-shaped, it's symmetrical, and it has specific kurtosis, etc. OK. Yes, sir. Yes, sir. No, he's stretching.
Will you say if there was a floor effect or a ceiling effect that it won't be normal?
That's very good. So the only condition under which where normality assumption is not fully guaranteed is when you have a severe skew in the original population, like this. You've got a skew here, and you run animation, and you're not going to have a normal distribution. So let's do it. Let's do it 10,000 times. And, well, it's sort of normal, but there's a little bit more of a tail here. Here we go. Yeah, if we run it enough times, you'll see it's not normal. There's some tail here. And you can tell it's not normal because the mean here, no, the means are equal. So let's try it this way. Maybe this makes it, yeah, it's still, let's see. Let's make it a really long tail, and that should do it. Yeah, so the tail, no, it's still showing you a little bit of a tail. It's still showing you a bit of a tail. Yeah, okay. So you see, it's pretty robust. I mean, that's one of the assumptions that it's pretty robust to the shape of the original population, but you get a little bit of lack of normality because of these tails here. Okay. So let's go ahead and answer. Are we okay with the battery? Okay, great.
It's like flashing, or it was.
Was flashing? Is it not flashing now?
No, it's only when you pause it, it is.
Oh, okay. So it's not paused now.